Welcome to the CWMP presentation on top 10 tips for wireless LAN design. My name is Keith Parsons, and I'm going to be your host for the next 30-35 minutes or so. That's the time frame, so buckle up. It's going to be like drinking from a fire hose. Just a quick slide about me. You can find me on Twitter, Keith R. Parsons on Twitter. I've been around the industry for a while. If you need anything, just ask. I love conversing with people via Twitter or via email. It's great. You can also go out to the WLAN Pros website and see a lot of stuff there. To get started, we're going to look at a view that I put together. It's a graphic on how to troubleshoot Wi-Fi. Wait, I thought this session was about how to design. Yep, this was about design, but we need to understand the process and the flow of how it works together. So if you look at the next picture here, we're going to be focusing on the red side. Your network infrastructure, local area network is the blue, and the WAN and the internet is the green. But we're going to be focusing on the red part of this. At the end of the slide, of this presentation, you can go and download this graphic and look at it yourself. I strongly suggest you figure out how Wi-Fi works. It's like the core of what we're doing here. And there's a graphic that helps you place things in space so you can understand how they all work together. Well, actually, we don't start with design, do we? We first have to start with define. What is it that you want? There's a definition stage. And personally, when I'm going to a customer, I'm going to spend half, maybe 3/4 of the entire design time and budget on the definition. Because if you can define it very precisely, the actual design part's really easy. So define, then design, and then someone does deploy. Now, some companies, the deploy is the same people. In my firm, we usually offload the deployment to some other group who pulls the cables and mounts the APs, etc. Then there's a validation. One of our rules we're going to cover here is about validation. Very, very important to validate your design. And then the last D here is diagnose. I've got 10 tips for you today. And yeah, I had some extra ones, so I put them in the front rather than the back. All problems will look like a wireless problem the minute you fire up the access point. So do whatever you can to make sure the wired infrastructure is working before you put that last component of the access point in place. Because as soon as you put the access point on the network, it becomes a wireless problem. And we know most problems aren't wireless problems, so why would you make it even worse? So I like to have in our installs, we build from the core out to the edge rather than reverse. Because if you put the AP up first, and then you pull the cable, and then you configure the switch, and then you configure the router, and then you get back to the controller, there's a lot of things that could go wrong. I would rather have everything except for the wireless working and tested before we get there. Another quick tip, delegate. We can't do everything. This is wireless LAN design tips, so anything that doesn't have to do with that, delegate it out somewhere else. Know your PHY. What's the PHY? The physical layer. You need to know how a NIC works. Now, NICs are entirely different in wireless than wired. We think of a NIC as something that just convert ones and zeros on one side into some form of media and send them on the other side. But if you start down at the NIC layer with Wi-Fi, you'll realize that the radio tap header is something that the receiving NIC adds to the frame that comes in. Meaning, every single device receives a different radio tap header. They may have different spatial streams. They'll be in a physically different location. They have a different antenna. So even though an access point transmits a single frame payload that's identical, every client that hears it is going to hear it differently. That's a pretty big change in what we're doing. We need to understand RF media, how it works, the whole modulation encoding scheme, and what happens when you change from a 20 to a 40 to 80 megahertz wide channel. That's changing our network. And don't get suckered. I don't know a better word to say. Don't get suckered into thinking there's something magic about 80 megahertz wide channels. They're obviously 4 times better. No, they're not 4 times better. The things about the PHY, spatial streams, modulation, coding, and the entire contention process are what's going to drive your design. Code channel interference? Wi-Fi 802.11 is 100 times more sensitive to other Wi-Fi than to non-Wi-Fi. It's built right into the protocol. So don't ignore the parts that Wi-Fi is the number one enemy of other Wi-Fi. It's going to have to come into your design process. You need to also understand how a single frame is transmitted, because if you don't, it's going to come back and bite you. In this picture, the only thing that crosses the wireless to wired boundary is the little teeny blue sliver. All the other parts take time. And again, in Wi-Fi, the thing we have least of is spectrum. And so if we can take the air time that's being used and make it more efficient, we can get more data to go over the same network. So if we want to solve for capacity, more devices attached in the same area, what we're really solving for is speed. If we can deliver faster data, we can make each user use less air time. And if they use less air time, more users can use it. So capacity is about speed. It's not about adding more APs. Yeah, AP salesmen would love you to know that, but that's not really what it's about. There is a chunk of time, in this example, about 38% of our time is just wasted in arbitration. That's because the protocol that runs under Wi-Fi uses this distributed coordinated function. Now, just if you take those words apart, you go, what? We're coordinated, but we're not. We're distributing coordination. Yeah, what we're doing is we made up a system that didn't require things to talk to each other in order to work. And it does it by using a whole lot of time to get there. There's a whole lot of overhead for RCS, CTS, and then we have our little teeny payload. And in front of the payload is some more overhead, 802.11 overhead. And then we have a CIFS-AC at the end to get a little block ACK that comes in. Out of all the time we spend in the air, a very small portion of it is actually going across the wired boundary. All the rest of the colors, other than blue, they're in the air, but they're not on the wire. Again, if you understand this, you'll also understand why it's really tough to get to a position where you need mgig to support APs. Now, you might want to use mgig. Nothing wrong with mgig. I like mgig. Please. But that's not the reason you don't go to mgig isn't because Wi-Fi demands it. It's just not showing up. Let's show another example now of the differences when we're looking at two different things. The first one up is going to be 20 versus 80 megahertz channels. And the second is what happens when we take the best possible Wi-Fi and compare it to the worst possible Wi-Fi. First up is 20 versus 80. The airtime, the contention to get the airtime, exactly the same for both of them. RTS, CTS, exactly the same for both of them. And in this color scheme, this is using a different tool. Green is the payload. And you can see as we went from a 20 megahertz to 80 megahertz, yeah, the payload went faster. All the other pieces didn't. So the actual net savings in time is very small. And I'm not even showing here that downside of going to 80 megahertz channels is you're going to lose 6 dB of SNR. Additionally, you're going to have a whole lot of the primary channel versus secondary channel and the OBSs overlap, all sorts of other things for this little teeny gain. Now, your end users, when they go to an 80 megahertz channel, they'll see this bigger number, but that number is only for the payload. We really need to be looking about the entire airtime. Now, the bottom of this slide, also very important, the bottom of this slide is showing what if we took a very poorly run Wi-Fi network. It was designed with only 6 meg for the management frames. 24 meg is the max we'll allow to go through for the data rate. We're not going to allow it to float faster. We're going to lock it only at 24. 20 megahertz wide channel, single spatial stream, MCS of only 3. That's a really poorly performing Wi-Fi. And then we're going to compare it to someplace where we put the control management frames at 24 meg. We allowed it to float all the way up to full MCS 9, 2 spatial streams, and you go, yeah, it's faster. Really? Not that much faster. The overhead is still there. Yeah, the control frames went a little faster and it took a little less time. But it's not 4x, 5x different. It's less than 1x differential between the fastest and the slowest Wi-Fi. Again, it's all about airtime. And the reason rule number 1 is know the phi is because that's where all these little things happen. Another thing that happens in your PHY is how does a client join? There's an entire process of how a client goes through association, probe request, probe response, authentication request, authentication response, association request, association response. And then the client can get on the network. And then at that point, there's either open, PSK, or .1x. That's the authentication portion. And then there's an encryption portion. And then we have port control. Then we hit the upper layers to get DHCP, DNS, VLANs, etc. Once you have all of that opened up and you can actually hit the LAN, then you hit the captive portal. So if you hit the captive portal, that means all of the 802.11 things are already working. A lot of our end users think the captive portal is the beginning. It's actually the end. So you should really understand how this whole flow works, and if you're troubleshooting where each of these things happen. I like to design with a open, no authentication, no encryption, no captive portal. Yeah, so I can prove it's not the Wi-Fi. Test your Wi-Fi separately and then add each of those other functions in that are on top of Wi-Fi. 802.11 is the blue 802.11 association. All the other things are on top. So design to make sure that works properly. The other pieces are actually more about other things, not the actual 802.11 itself. There's a whole lot of requirements, and we usually get a requirement from our customers who come in and say something like, we just need the Wi-Fi to work everywhere fast. Yeah, it doesn't work that way. Not to mention, we can't design Wi-Fi for all Wi-Fi clients. Just as an example, iPhone 1 had Wi-Fi. Now, if you were going to design to make it efficient for an iPhone 1 today, you're designing for 2.4 gig, not for 5. And that's just one thing. It had a bad antenna, the bad chipset. Years go by, and those older chipsets, slower, yeah. Use more airtime, yep. More airtime means less density. So we can't hit capacity if we're designing for those older devices. So we need to know which device we're designing for, which one device we're designing for. Now, if we pick the right one, hopefully all the other ones will come along. So you need to know all your requirements. Now, I put on the slide a couple of groups here. The group in the green box are the things that you can put into your design or validation tool. Primary coverage, secondary coverage. Some people call that overlap. Yeah, I don't do that anymore. And if you want to look it up, there's a fallacy of channel overlap, a white paper I wrote probably a decade ago now about how we don't do overlap in percentage. We do overlap by dBm. Also, what goes in which frequency? What goes in 2.4? What goes in 5 gig? If you allow your customers to answer this one, they will eventually, if you give them enough help, get to the point where they realize the only thing that should be in 2.4 are 2.4 only devices. You get to use only 2.4, they stay together. The only thing that should be in 2.4 are the 2.4 only devices. You don't want a 5 gig capable device over in 2.4. He'll have a bad day. One, going to 2.4 means he'll have a worse day than he had in 5 gig. Not to mention, he'll be taking away a slice of capacity from something you can't go anywhere else. Bad, bad. Don't go that route. Another thing we should look at is co-channel inference. We should design for it. We should measure for it. We should validate it. It's the killer of Wi-Fi. I can just throw up AP after AP after AP. But if you have two APs on the same channel and they see each other, you have the capacity of one AP. Actually, a little less than one AP because they're going to be sharing. So co-channel inference, you definitely have to put it as a requirement. You design to it, you validate it, and you make sure it stays as far away from your network as possible. Device to radio ratios. There's not a lot of devices that say this. When you buy a Chromebook, it doesn't say no more than 17 Chromebooks per SSID or per radio or per AP. They don't say that. The things that really need that are usually voice over IP handsets, and they do. Part of the reason they do is because the way they use the PHY and QoS. So figure out what your device is, what it specifically needs, and make sure you give it what it wants. Both primary, secondary, co-channel inference, data rate, SNR, all of the things. Now, I'm not one to dwell on terms like, is this area high density or low density or medium density? I don't care about density. What I care about is what's the requirement. For a school, the main requirement might be all the classrooms. If there's 30 devices in the classroom or 50, I don't care. That's the requirement. So that's normal density. What I care about is special density areas. In a school, it might be the auditorium. In a hospital, the normal rooms, the hospital rooms, that's normal. But if you go to the nurses' station and nurses congregate there, now that area is special. So it's more about designing to make sure you meet where the special density is. A stadium, that's normal density for a stadium. You go out into the walkway or to the tunnels, that's a special density because you have a different density than where people are. So think about those. Now the ones on the right, jitter, latency, end-to-end QoS, there's a whole bunch of things over here. We don't measure these with our Ekahau or Tambosoft or Air Magnet. They're more of a vendor specific. They're still valuable. They're still very important. You need to know them. They're a strong requirement, but we're just going to measure them using different types of tools. So this one, it's all about the requirements. It's not about the green. On Twitter, I don't even know who they are, but there is a Wi-Fi Hulk. And whenever someone mentions green, there's a little Twitter message about being the Hulk because people say it's green. It's not about the green. I can make any Wi-Fi look green. You just adjust the values. I can make it look purple or blue, whatever I want. Just being green doesn't mean it's good. Green doesn't mean good. Now, an example here, this is from a high school. We went and did a survey in a high school. We put a bunch of APs up. We did a bunch of testing. In a minute, I'm going to tell you about the testing, but let's just look at these two little heat maps. The one on the left is from a MIST 43 AP. By the way, both APs are at the exact same transmit power. The one on the right is a Cambium. They're both Wi-Fi 6. The MIST one on the left happens to be a 4x4. The one on the right happens to be an 8x8. Now, if you looked at just the green, now again, these both have the exact same scale, and they were collected with data from the exact same survey. And you look at the Cambium on the right and go, whoa, that's really bad. Look how quiet it was. Neg 80, all the way out there at 100 meters. By the way, this is on a football field, but we stopped at 10 meters, 25 meters, 50 meters, 75 meters, and 100 meters. And then you compare the data. When you look at the data, the MIST ones on the left is in green, pretty decent at 10 meters, doing 120 meg data rate. Yeah, good stuff. Now this was a combination where the data came from is a combination of a MacBook, a Lenovo with an AX chipset, a Wi-Fi 6 iPad, and a Wi-Fi 6 iPhone. This is the average data. And you can see the one on the right, the Cambium, outperformed the one that was more green. It's not about the green. It's about what are you actually going to achieve. So strongly, strongly recommend you test what you're doing. How do we do these tests? The last slide, I showed you some test data. Yeah, we wanted to do testing. Testing's important, but we didn't want to use like really expensive exoteric kind of things or a Faraday cage in a lab. So instead, we went out to a football field. We got access to a high school football field. They're 100 yards long with two 10-yard end zones. But instead, we switched it up to meters, and we counted out how many meters it was so we could be more international. We set up some APs on one end. They were up about 1.4 meters high off the ground. We did surveys, lots of surveys. We walked with an iPad, with an iPhone, with a GPS, with a stop and go, with a continuous mode, all sorts of things. We did a back and forth horizontally, following the lines on the field, but also vertically going north-south. We did it with the device on the hip, on the head, in different locations. We followed around with a drone. We got some drone pictures to show you of the site. We did a time-lapse video of while we're there so you could see what we're doing. The goal was to go on site and use normal equipment. We just took some APs that we had in our labs, normal laptops, just the ones we had, and then we took a pair of WLAN Pis. Now, WLAN Pi is just a little handheld device. We happened to have one with us on site, and it was our local server. We put another one back at the school district's corporate site, so that was our remote server. And then we did different kind of testings. So testing local was client to AP directly to the WLAN Pi. We were using a HTML5 test deck. So we weren't doing speed testing out on the internet. We were controlling it all on our side. And you can run the same tool on your own equipment anytime you want. We wanted all of these tests to be totally repeatable. And so you can test them yourself. So in this test, we did test local. We also did test remotely so we could tell the difference between a WAN link and a WLAN link. The examples I just showed were what's the WLAN link? I want to know how I'm doing from client to AP directly to the test. I don't care about the backhaul. Now, we did some testing on other backhauls as well. But if all you're trying to do is compare AP to AP or client to client, you want to have it local there. Number 4, follow best practices. Now, how do you know what best practices are? First of all, you can go to the vendors, whichever vendor you're beholden to, whichever one you're installing or testing or using, and they have best practice guides. Now, some of the best practice guides don't always match each other, but if you try to meet what your vendor says to do, it helps a lot. You could also learn from industry leaders, from other people who are presenting at this conference, people who present at the WLPC conference, other vendor conferences. There's lots of presentations you can get. We have tons of videos on the WLAN Pros website. Now, in our industry, we have a term, bad fi. I don't know if I like the term, but do your own testing. Just because someone said, well, the best practice is never hang an AP on the wall like a clock. I've said it myself. I think it is the best practice to never hang an AP on the wall like a clock. Have I broken my own rule? Sure. There are times when you need to break the rule for certain reasons. So don't be afraid to break best practice rules. In fact, I encourage you to break best practice rules as long as you know why you're breaking it. Just because you saw somebody post it on the internet and there's a cool, oh, look, you can do this with an AP. Yeah, Wi-Fi is so extremely resilient that even when you do it wrong, it still works. So just because it's working doesn't mean it was the best practice to do. Use your best judgment and adapt. Use the best practice until you can show that there's a reason you changed the rule. You put an AP on the ceiling rather than on the wall, not just because it was a best practice, but because you tested it. You chose to not put APs in hallways, not because Keith told you so, but because you can see that there's an actual benefit to doing it. Best practices are just that, they're recommendations. If you follow them, usually, most of the time, you'll have a much more efficient Wi-Fi. Yeah, this is one that I'm just going to say it right out. Don't do it. Don't follow marketing ratios. They're not engineering, they're purely marketing. 1 AP per 2,500 square foot. Well, maybe on average in that building at that time, no, that's not engineering. That's not design. That's just throwing stuff on a map. I even know some vendors who just tell you, oh yeah, high densities every 2,000 square feet, low densities every 250 square meters. They just have throw these numbers out. It's the people who are trying to sell you things that tell you that. Don't do it. Use the tools, use math, like real math, free space loss math, etc., to figure out how to do it. Now, here's an example. I show this example a lot of times, but hopefully it'll help you understand. If you were going to design a little doghouse, you go down to your DIY store, you buy some wood and lumber, you might sketch it out on a napkin, and you hammer it together. It's really actually easy. You don't have to have a super design. And I doubt you would do a snow load analysis on that little roof, or how much wind it can take on the side, or whether or not if the dog bumps into it, it's going to collapse, the size of the screws you need to put it together. You just build it. Wi-Fi is a lot like that. When Wi-Fi is small scale, you put an AP in your house. Done. You got a bigger house, you put 2. That's very simple at the small scale. But as Wi-Fi scales larger and larger, it gets more and more complex. Like this bigger barn. Instead of dogs, what if we had horses? They're a lot bigger, and so now we need to build the barn bigger. It's still made out of wood, but now we have to deal with wind, snow, rain. How much weight can it hold? What kind of gap is it? And if I exceed a certain size, I have to go from a truss to a glue lamb to a steel frame. Yeah, that's all engineering. Wi-Fi is like that. The larger you get, the more complex it is. And so don't use a ratio, 1 AP per classroom. Yeah, I know. You can make 1 AP per classroom work. You can make 1 AP per 2,000 square feet work. You can make Wi-Fi do anything you want. That's not the hard part. The hard part's making it efficient. And that means using engineering tools. Always, 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 always validate what you're doing. Now, there's a lot of different ways you can go through validation. You could do an AP on a stick. When you do an AP on a stick, you actually put an AP up on a tripod. Now, you can do this before you design as a technique to measure RF attenuation of the walls, to measure how if the maps you were given match. You can do an AP on a stick after you design to validate the design. You're not validating the install. You're validating, does the design still meet my requirements? Now, I like to do validations post-install. Now, in the post-install validation range, there's 2 big categories, active and passive. You always have to have a passive. In fact, Ekahau makes it so you can't do an active without having a passive. Passive, the most important. Passive means I'm listening to everyone, neighbors, mine, my SSID, somebody else's. I want all the information I can gather together. Compared with an active is when you have your client device associate to an AP and you're either pinging or sending iPerf data. Realize the active survey data you receive is going to be extremely flawed. Because think, every time you're near an AP and you walk away, the signal strength gets weaker and weaker and weaker. Your ping times get higher and higher as you walk away. And then all of a sudden you're right here and you're next to the next AP. As soon as you associate it to it, it's amazingly fast. And so you get with active surveys is this degradation as you walk away from one AP, a little break, and then really fast as you associate it to the next AP. If you did an active survey clockwise, looked at the data, you would see it skewed. There would be a tail going away from every access point in an active survey away. When you went toward an AP, you're not going to have any active data because you were on the previous AP. Now, there's nothing wrong with active data. It just doesn't tell you what you think it tells you. You think the active survey is going to say you, a user here will receive this. Totally false. You're walking some weird path that normal people don't do. You're collecting data from APs. You might skip 3 APs because you roamed over them. Just realize active survey data, suspect, and every time you roam, you'll get a drop. And so if you're plotting out ping times, you will get drops every time you roamed. That does not mean that location is a bad Wi-Fi. You might have fantastic Wi-Fi there. It just happens to be where you did that little roam. Stop and go versus continuous. I love continuous. I hate stop and go. Stop and go's for losers. Stop and go's for people who don't mind throwing away their data. Because when you collect data with a continuous, every time you walk, click when I start, click when I stop, click when you turn. Very simple rules. It's all you have to need to know. And you go everywhere. All the data in between every one of those clicks is being collected. You flip into a stop and go mode, you click, you wait, takes a longer time. You then, when you're done with the stop, the go part is you're walking. And you know what happens as you're walking? You're throwing all the data away. You're collecting data. The data is actually being collected right then. And you decided, since I can't walk in a straight line and I don't know how to click when I start, when I stop, when I turn, I'm going to willingly throw all that data away. All you have to do to see this is look at your data set and you will see that. Stop and goes, use continuous mode. Now in continuous mode, we have other choices. We can go autopilot. We can do GPS. We can just walk and click. You can use an iPhone, an iPad. There's all sorts of ways you can go around these. Always choose the APs before you start designing. The reason you need to do it before is there's such a huge difference in access points. There is no generic access point you can design for and then install and have it match. It just doesn't work that way. So one, I wish there was never a generic AP allowed because you can't buy one, so why would you design for it? Now in the example here on the slide, in the upper left, you see a 10 dB is the transmit power that's leaving the rate that's going into the radio. The radio then sends it through its antenna, and what we get out is EIRP. In this case, this AP had a negative gain on its antenna. Totally possible. A lot of phones and handsets do, but this is an access point. By the way, all 6 of these access points, they're all sold into the exact same market. And if you pick one and it's the wrong one, you might have more APs or less APs. The one on the bottom right, we put 10 dB in and we get 18, almost 19 out. It has a positive 9 dB. And then you go, well, how can they do that? Well, if you look at the antenna, you can see the instead of wasting energy going up and down, it's only focusing in a certain direction, and you get a better gain. Yes, this means you need fewer APs. This is just one example. I can show you tons of examples when you go on site, put it up in a football field, walk it, and you can see there is a huge difference between the APs. The previous one I showed you isn't always about RSSI. There's other things that APs have, spatial streams, better MCS, better firmware that allow you to change. Design for your clients you have, but also choose your AP before you do any other design. 8 is meet all your requirements. Not just primary coverage, not just secondary or co-channel interference. There's an entire list of things you need, not just the list I show you. There is clients need to see a certain throughput. The roam times have to be down. But the number one cause I've seen in my career for remediation calls, co-channel interference. Co-channel interference causes capacity to drop. You think adding another AP adds capacity? Most of the time it actually drops unless you can prove that it's not in the co-channel interference zone of anything else. This is a good time to talk about cabling. Cabling, I thought this was Wi-Fi. Yeah, let's just do a little side jump over here to cabling for a minute. If we look at the evolution of cabling, silver satin, Cat 3, Cat 5, Cat 5e, and then finally Cat 6, what did we do to make our cable go faster? It's literally 1,000 times faster. The copper is the same. We use the same copper. We use the same RJ45 head. The distances are the same. What we changed were things like pinouts, twist ratios, dielectric that went inside. All of those combined show what we were really changing was we changed the interference, self-interference, a cable interfering with itself. And by getting rid of self-interference, we made it go 1,000 times faster. What do you think we need to do to make Wi-Fi go faster? Lower interference. What's the number one cause of interference for Wi-Fi? Other Wi-Fi. Back to the co-channel interference. Design around it and you can make it go fast as well. Understand how capacity really works. You can't just go draw a little box on the screen and say there's 27 clients in here and here they go. Yeah, all of that software, whether it be Andrew Vanage's capacity planner or any capacity planner built in any piece of software, they all make one huge fatal flaw. They make too many assumptions. They assume that an AP has a certain amount of capacity. APs don't have capacity. The RF has a capacity. So if I have two APs on the same frequency, they're sharing the capacity, and yet all of the capacity planners mess that up. So understand what's really there. Realize what each of those assumptions is. You can still work on capacity, but it is not nearly as easy as you think it is. It's not just a quick calculation. We have to understand the design and whether or not there's co-channel interference, and we have to minimize that first before we can ever get to capacity. Yeah, this is CYA. Document everything. Document it for yourself, document it for the future. I really like documenting all the requirements. So when they call back 3 years from now and they say, this doesn't work. And you go, really? Does it match the requirements we designed it for? Well, yeah, but we got new stuff. Oh, so you want to change the requirements. And I love handing over to my customers when they ask for things like, we want you to put them in hallways. We want them below the ceiling. We want it, whatever they ask for. And if I know it's going to make a bad design, I just have them sign a document. Yes, Keith, please design me a poorly performing network. I've actually had people sign it. Usually they get a little gun shy and say, well, what do we really need to do to fix it? If you need more of these and more of the tips or any of the graphics, come out to WLANpros.com. We'll see you in the community.